Hello, I'm Robert from Doomsday Debunked, and I'm just going to clarify. Apparently, a couple of things weren't very clear in the last video. So, what these stars actually are, and so I'm going to present just very simply the main points. So, the first kind of gamma ray burster is a couple of neutron stars. Now, neutron stars, they are a star that is quite a bit heavier than our Sun. Will eventually, when it collapses as a supernova, then it ends up in a very, very dense state that is made of solid neutrons, hence the name. It's no longer really a star in the sense it's not actually burning any fuel anymore. It's just the hot remnants, which very quickly cool down for neutron stars. And the neutron star is very small, about 10-15 kilometers across, about the size of a city, but very, very heavy. And as you can imagine, something so small, it's not very easy for such a small thing to hit another small thing of the same size. But it does happen, and they sort of spiral around each other, and but only and these ones. So the nearest of any kind of gamma ray burst that we spot is, unless there have been new ones found to be nearer, but they are about 50 times the distance to Andromeda Galaxy, which in turn is about 2.5 million light years away. And so it's like sort of 50 or so, or several dozen galaxies away in that direction, very, very far away. This, of course, our nearest big galaxy is the Andromeda Galaxy. And it's gravitationally affected by ours. But anyway, so those the neutron stars. These are the ones that are high energy at their peak, but they're very short bursts. These are the ones that produce muons, but not enough, the heavy electrons, which are the only things they produce that could go through the atmosphere, but not enough of those to to harm us. And the total amount of energy from these is rather low, so they have to be very close to us to cause any harm of the long-term nature. And for both kinds of stars, then it's not the idea that the gamma rays can't get down to the surface. The atmosphere is opaque. And the muons, then they're no longer an issue. And the old idea was that the ionizing radiation creates and destroys the ozone layer. It also creates nitrogen oxides of various kinds, which then keep the ozone layer destroyed, and this lets lots of UV through down to the lower atmosphere. And the idea was that this would produce ozone down here, because it's no longer being produced up there. It's UV that makes the ozone layer. And then when that happens, then that what was thought would be able to harm life. But we now know from more detailed modelling that not enough is produced to be harmful. So we don't need to worry about this whole scenario. And so really it's just the UV coming down to the surface that's the only thing that is now a concern. And if one of these, that's sort of 8,000 light years away, were pointed towards us and point exactly at us, it's a bit like very strong solar storms. Then we'd have the ozone layer being damaged, and then as a result of that, then we get more UV, so we need to protect ourselves against UV, and we need cataracts, glasses to prevent us getting cataracts. But that's not something that we need to worry about, as I explained, because these small ones, they're very, very rare. They have to be extremely close to cause any harm, and it's just the nearest, and the galaxy is so big, and we haven't had a single one in the entire galaxy. And so for those little ones, we'll be able to be right close, sort of in the pixel of the sun in this picture. And but for the bigger ones, they can harm us from a greater distance. So the bigger ones, they are very easy to spot. And remember, we haven't had either of those in our entire galaxy, while we've been spotting them flashing away in space from other galaxies, because we can see them from such a great distance. That's why we can see so many. We can see them, dozens of galaxies away, thousands of galaxies away. We can see these things. But the closest any has come is about 50 times the distance of the Andromeda Galaxy. until it turned 2.5 million light years away. So, if one happens in our galaxy, most likely it's somewhere way out there. And the really big ones, so the other kind of star, these really big ones, and they look like, I'm going the wrong way. Well, this is from one of them. This is a spirally thing, but I think the Homunculus Nebula gives a better idea of kind of the scale of its Zeta Carinae. And it's a big. This is the size of the solar system. The star itself is right in the middle there, hidden by the dust. And it's a big, very young star. Goes through its life very quickly, and these are very, very obvious stars. There can't be any really close ones. And we only know of 3 at a distance of 8,000 light years. The last one was a bit of a surprise when it was discovered. You could have a bright star like that sort of hidden in a thick dust cloud at some distance. But I mean, if it's obscured as well and hard to spot, and that again means there's stuff in between it and us. So I don't think you need to worry too much about even if there could be another one there. And these there are only these 3 that we know, and as I said, all 3 of them are pointed the wrong way, and not point towards us. And there's only one, APEP, which is not on this page. It's the only one that's even really likely to be a gamma ray burst, because going back to our galaxy thing, then because it's the wrong kind of galaxy. It's got, just because we're here, and the carbon and oxygen and and nitrogen and so on that makes up our bodies, that shows that we're in the wrong kind of galaxy to have the very big stars producing gamma ray bursts, except in the very unusual situation of APEP, where it seems to be due to 2 very young stars that form close enough together and actually collided with each other and then span up very, very fast, so fast that it's almost blowing apart due to the speed that it's spinning, or the resulting star is spinning. That's an extremely unusual situation. And but anyway, there's nothing like that close enough. And if you think about it, imagine it's not even the edge of that circle. It's further away, something like about that distance away. I don't know where they are exactly, but somewhere in the galaxy at that distance, about a third away from here to there. And then pointing in some random direction, just randomly in space. If you have 3 of those pointing in a random direction in space, it has to be very narrow beam, sort of like the thickness of this thing, to actually be significant. The more focused it is, the further away it can harm us, but then the narrower the beam has to be, so the harder it is to point. So you would expect 3 at that distance. If that's what you would expect, that it's very surprising if even one of them was pointed directly towards us. And then the evidence is pretty clear that they all pointed away, except just possibly Eta Carinae, but it's got so much dust in the way, we don't know which way it's pointed, but again, it's very unlikely it's pointed our way, and if it is, there's all that dust in between. So that's why we don't need to worry about the big ones, because there just aren't any that are pointed our way, and the little ones, they're just so rare, and they have to be so close that, and we only spot them dozens of galaxies away. So sometime, millions of years in the future, more likely, not so likely that it happens anytime soon, then we are sure bound to get the gamma ray burst somewhere in our galaxy. But it's extremely unlikely that even then that it is anywhere near to us. So I hope that's a bit clearer. Got it down to, that's quite short, so hopefully that helps.